Hello and welcome to the Manhattan Project National Historical Park in Los Alamos, New Mexico. Today you get to see a demonstration of a chain reaction. A retired Los Alamos National Laboratory physicist, Dr. John Pratt, will demonstrate the process. The key to the entire Manhattan Project effort was a chain reaction of nuclear fission. So, let's take a look at nuclear fission. Here's a slide with a uranium nucleus. Let me give you a bit of scale here. You could line up approximately 40 million uranium atoms across your fingertip. And remember that uranium is the biggest naturally occurring atom we have. Like all atoms, the uranium atom would have a cloud of negatively charged electrons around a nucleus made up of positively charged protons and neutral neutrons. Each atom normally has the same number of electrons and protons, making it electrically neutral. The electrons are where chemistry takes place. The number and arrangement of electrons determine the chemical properties that define elements. The nucleus is roughly 1/10,000th of the size of the atom, and the atom is mostly empty. And the diameter of this uranium nucleus is roughly 7 times the size of that neutron coming toward it. And this is an approximation. So the uranium nucleus absorbs the neutron and breaks into two completely different nuclei, which are called fission fragments. These fission fragments are almost always intensely radioactive. Here, the important feature is the release of energy, about 100 million times as much as released in a single chemical reaction, such as burning or explosives. Now, one reaction, even one this strong, does not deliver usable amounts of energy, but the fission also released neutrons, averaging approximately 2.5 neutrons per fission. It was completely discovered that these neutrons can also cause fissions, leading to a chain of fissions or a chain reaction that releases energy with every step in the chain. So now let's see a demonstration of a chain reaction. There's a classic demonstration with mousetraps acting as the part of uranium or plutonium nuclei. And these are the colored porcupine balls acting the part of neutrons. Here we have some mousetraps, all thanks to our intrepid volunteers, and each holding about 2 or 3 of the neutron balls. We did 2 or 3 balls per mousetrap because the fissions release an average of 2.5 neutrons. We can drop in a neutron to start the chain reaction, just as nature would do for a uranium chain reaction, or we can start it like a plutonium chain reaction. Remember, plutonium is man-made, and when the plutonium-239 is made, a bit of plutonium-240 is also made. So for this demonstration, we have to trip a mousetrap of plutonium-240, and we will let it start the chain reaction. 3, 2, 1, start.
Go.
Rather quickly, most of the mousetraps got tripped, and then our chain reaction ran out of fuel. Did you notice that many of the neutron balls hit the box and bounced back into the plutonium mousetraps. That is called reflection. What would happen if we did the same experiment without the box to reflect the neutrons back into the uranium or plutonium? So we reset the mousetraps and took away the box, and we'll do that experiment. So here we go without the reflector. 3, 2, 1, start. Well, that was a bit different now, wasn't it? Notice that this time we have some mousetraps that didn't snap. We say the reaction was less efficient because it didn't burn up as much of the nuclear fuel. We saw that the reflection causes more fissions. Now, if you are more interested in science or information on chain reactions or the Manhattan Project National Historic Park story, please come to Los Alamos, New Mexico, and see us.